So I want to indicate how the discussion that we've been having about Bott periodicity for the unitary groups generalizes to the orthogonal and symplectic case. It's very beautiful. So I remind you that we have kind of the easy vibration, where we have unitary goes into contractible, goes down to the Grassmannian. But then we had the hard part, which, so this in particular meant that the Grassmannian that if we take loops on the Grassmannian, then that's like unitary. But the hard part was to show the other way, that loops on unitary is like the Grassmannian. And so remember, we used Morse theory applied to the classical mechanics of a particle on a group manifold. So we have this action where G maps into the group manifold, and that way we can study paths on the group manifold. That's homotopy equivalent to loops on the unitary group. And then we found that those are the minimal action loops were given by Grassmannians. So now we're going to try and apply the same strategy to loops on the orthogonal group. So let's see what happens. So now we look at, let's call it P sub O to N, which is the space of all paths from +1 to -1 in O to N. And so again, we have the action for path G of t is minus the trace of G inverse G dot squared dt. So that action, we can apply Morse theory to that action. And once again, the solutions to the equations of motion, which take us, this is, our time is going to run from 0 to 1. The equations of motion are solved by G of t equals the exponential of pi t times a, where a can be now skew diagonalized. Remember, A is in the Lie algebra of O2n, which I remind you is the set of matrices M such that M transpose is minus M. That's the Lie algebra of O2n. Okay, so therefore, A can be diagonalized, skew diagonalized, to be of the form 0, A1, A1, 0, plus 0, A2, minus A2, 0, plus dot, 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 plus 0, AN, minus AN, 0. And by choosing H suitably without loss of generality, we can say that all the ANs are positive. Okay, and then this will satisfy the boundary conditions. Clearly, at t equals 0, this is at 1. We want this thing to be equal to -1 at t equals +1. And so the AIs are odd integers. And if we take the AIs to be odd integers, then g of 1 is equal to minus 1. Well, once again, we can calculate the action for these solutions. So S of g of t is then some constant, doesn't matter really, 2 pi, I think, trace of minus 2 pi times the trace of a squared. Okay. I shouldn't obsess about these factors of 2. They're not important. This is 2 pi times the sum of the AI squared. Okay. So once again, the minimal action paths have all the AIs equal to 1. That is to say, minimal action implies that a squared is minus 1. Okay, that's very important for what I'm going to say. Okay? So the minimal action paths satisfy a squared is minus 1. Now, as I said, A is in the Lie algebra of ON, so A transpose is minus A. So also, A transpose times A, this is for minimal action paths, A transpose times A is equal to 1. You see, because A squared is minus 1 and A transpose is minus A. So that implies that A is also in the orthogonal group. Okay, a little surprising. It started its life in the Lie algebra, but because of this minimal action condition, it's also in the orthogonal group itself. Cool. So that means that we can identify the space of minimal action paths with what I'll call omega sub 1 of 2n, which by definition is g in O2n such that g squared equals minus 1. And by definition, that's some submanifold of O2n. Now, once again, one can show that the number of unstable modes of higher action paths is greater than or equal to 2n minus 1. The important thing is that it grows with n. So, by Morse theory, as we explained last time, by Morse theory, for large n, omega 1 of 2n is a good approximation, topologically, to the loop space on O2n. Okay, I'm not going to show that. You can see that in Milner's book. But what I do want to do right now is understand a little better what this space omega 1 to n is. So, what is this space? Well, it's a homogeneous space for O2n. Because you see, if G satisfies this condition, then so does H inverse GH for any H in O2n. Right. Okay, moreover, every antisymmetric matrix can be brought by an orthogonal transformation to this skew-diagonal form. That's a theorem in linear algebra. Those of you who've taken my group theory course know that. So that means that the action is transitive. Okay, so that means that omega 1 of 2n is a homogeneous space. So let's calculate the isotropy group where. Well, good choice for where to compute the isotropy group is this element. J. Okay. So you probably recognize this J as something which defines a complex structure. So J squared equals minus 1, and this determines a complex structure on R2n. You see, if you, there are various ways of saying that, but maybe the most intuitive way is that if you tried to diagonalize this J, you would be making a choice of Z1 equals X1 plus IY1, and so on. And so then we can ask, what's the isotropy group? Well, the isotropy group is going to be linear transformations. So this defines an isomorphism of R2n with Cn as a complex vector space. And so the isotropy group are going to be linear transformations that preserve the complex structure, that are holomorphic. And that's, of course, just a copy of UN, where the UN is embedded into O2n. Well, by taking any complex number Z to x, y minus y, x, if x and y are the real and imaginary parts of Z. So what I've just said is that omega 1 to n is the homogeneous space O2n mod UN, or is at least isomorphic to, diffeomorphic to. So that's the minimal action paths. In fact, this space, essentially because of what I've said, has the interpretation as the space of all complex structures on R2n compatible with the Euclidean metric. Now, so that's an interesting space. I can't resist saying that if we took n equals 2, then we would have O4 mod U2, which is 2 copies of SU2 mod U1, which is something we've seen a lot of before. So this is CP1. This would be, say, CP1 bar. And so this is known as the twistor sphere. So in the particular case of 4 dimensions, there's a sphere's worth of complex structures on R4. Okay. There are 2 components because there are 2 orientations you can take. That's really just an aside from what we're really interested in today. But of course, it leads to a whole great science. Now, the main point I want to make here is that in the unitary case, when we took the loops on the unitary group, then by the same type of arguments, we found that the minimal action paths was a certain homogeneous space. It was a Grassmannian. but it was sort of the original Grassmannian we had started with. Okay, the Grassmannian whose loops on it was the unitary group, and therefore that closed the cycle. And so Bott periodicity was period 2 in the unitary case. Now, in this case, we should compare this, if you like, you could call it a Grassmannian, this homogeneous space versus O of n plus m over O of n times O of m. And the point is that they are just different. They're just plain different. Okay? They just have different homotopy groups. So, you see, so the cycle doesn't close at this point. So we have to keep going. Well, that was a good idea. Okay? So you might, if you were a loser, you might have said, well, it doesn't work, give up. But that's not the right thing to do. The right thing to do here, which is easy to say in retrospect, is to study loops in omega 1 of 2n. Okay? So if you first you don't succeed, loop again. Right? So we'll study loops in omega 1 of 2n, or equivalently, paths from j to minus j. Okay, so now we're now looking at the mechanics of a particle that's moving in this homogeneous space. But because of what I said before, this homogeneous space, we can and should think of it as a submanifold of O2n. So we could take our particle action now to be minus the trace of G inverse G dot squared, but now we would add a Lagrange multiplier, lambda G squared plus 1. So we have a constrained mechanical system. So, okay. So what can we say about these paths which go from J to minus J? So it's useful to calculate the tangent space at the point J to omega 1 to omega 1 of 2n. And now I claim that's the set of matrices. Yeah, I think there's a misprint in the notes. I should write the set of matrices in O to n. I wrote 2n by 2n real matrices, but it being, certainly it's in the tangent space of the orthogonal group. So if you look in the notes, I wrote A and M2n of R. I should have written O2n when I wrote it on the board. Okay, so why is this? Well, okay, so let's take a curve, g of t, which goes through j at t equals 0. So g of 0 is equal to j. And it's a curve through this manifold, so g of t squared is equal to minus 1. So now differentiate this equation and set t equal to 0. So you get g dot times j plus j times g dot. And equals 0. There's something that's confusing me. explain what's confusing me, and maybe that will help solve my problem. So let's supposing we take a simple path like g of t equals e to the pi t a times j. So then that becomes, that is equal to j at time equals 0, right? Now we want to say that g of t squared equals minus 1. So that means that e to the pi t a times j, e to the pi t a times j equals 0. Good. Now let's minus 1, thank you. Now what we should do is we should differentiate this at t equals 0, or equivalently look at the first order term in t. So the first order term in t is obviously a anti-commutator j is equal to 0. Now what is bothering me? What's bothering me is that if I take this g and write g dot equals pi a e to the pi t a j, and then set g dot of 0 equals pi a j, oh, it's okay. It's okay. Then it does indeed satisfy that. Okay, so.
Sorry, question?
Yeah.
So you have another constraint, right? Like gt times gt transpose equals 1.
That's right. So that means that this A, okay, that means that this A is anti-symmetric. So I could equally well have written this as A in M2N of R, such that A transpose equals minus A, and A J equals 0. See?
That's a small O.
Pardon?
A is in the Lie algebra, small O. The little O.
That's right. So A being in, this is a little o. That's my notation for the algebra. Small letters, small Latin letters. Okay, so this is the property of being in the Lie algebra of O2N. Okay? No, not capital O2N. Those differences are extremely important. Okay. So, indeed, I hope I haven't confused people, but I hope, is it, so I stumbled here. Is it clear what I'm saying? That this is the tangent space? That the g dots, the g of t, to first order in t, yeah, let me say it that way. Any path to first order in t can be written that way. And then, you see, if I have a path like that, then g of t squared equals minus 1, if and only if a times j, a anti-commutator j is equal to 0. So, in fact, so g of t equals e to the pi t a satisfies, times j, satisfies g of t squared equals minus 1 if and only if a anti-commutator j is equal to 0. Okay? Now that tells us something nice. That tells us that if we solve the equations of motion in O2N, then the solution, and A is in the tangent space at this J to this omega 1 subspace, then the solution in O2N remains in omega 1 to N. So, you see, that's a little surprising, right? So it's a submanifold. So it has this property, which if we were talking about geodesics, would be called the totally geodesic, right? So if I have a submanifold of a bigger manifold, it's not necessarily true that the geodesic in the submanifold is always the same as the geodesic in the bigger manifold. Right? I mean, imagine a one-dimensional world which is, you know, like this. Then in the blackboard, the geodesic would be that, but in the submanifold of this one-dimensional curve, the geodesic would be much longer. So what I'm showing is the analog of that for omega, the analog situation of omega 1 inside O2n. I'm saying that if you start out tangent to this space, then in fact the solution of the equation of motion in the big space is also the solution that remains within this submanifold omega 1. Now, therefore, the Lagrange multiplier is 0 if you go through this with Lagrange multipliers, and therefore the action, the on-shell action, is again minus pi times the trace of a squared. It's pi squared, but as I said before, the constant doesn't matter. The important thing is the minus trace a squared. Okay? So now what do? When we apply the Morse theory yoga to this, well, we're looking for the minimal action paths. So again, if we want to solve the boundary conditions, so again, if we have e to the pi t a j, which is going as a path from j to minus j, at t equals 0 to t equals 1, this a will be conjugate to 0, a1 minus a1, 0, and so on. And so minus the trace of a squared is the sum of the ai squared, another factor of 2. So for the moment, let's put 2 and pi over 1, okay? So the minus trace of a squared is the sum of the ai squared. So the minimal action paths are given by a such that a squared is minus 1. But that means that, again, a, remember, it's in the Lie algebra, but it's also in the group. Right? Same argument as I had before. So, cool. We can now say that the minimal action paths in omega 1 to n is a space I'll call omega 2 to n, which is the set of A now in big O to n, the orthogonal group, not the Lie algebra, such that a squared is minus 1 and a anti-commutator j is 0. And now this omega 2 is a submanifold of omega 1 of 2n, clearly, because if I just drop this condition, I just get into my definition of omega 1 2n. A squared is minus 1, so it certainly sits inside omega 1 2n. And that was sitting inside O2n. Now, let's interpret this a little bit, just the way we interpreted the previous guy in terms of complex structures. So let's set J1 by definition equal to J, and choose any J2 in this omega 2 of 2n. Choose anyone you like. Okay? Make your choice. And then also define J3 to be equal to J1 times J2. What do we observe? We observe that J sub I, J sub J, is minus delta Ij plus epsilon Ijk, J sub K. Where little I, J, and K go from 1 to 3. Okay? So that's something for you to check. You see, J2 squared is minus 1, definition. Okay? J2 and J1, by this condition here, anti-commute. Now, given those two criterion, you can see that if you define J3 by this equation, J3 squared will be minus 1, and J3 will anti-commute with J1 and J2. Well, what have we found? Anybody?
Quaternionic structure.
Exactly. So, just the way before we found a complex structure, now we found the quaternionic structure. So actually, there's a little subtlety here. I should have said that n must be even. You see, if n is not even, then this space will be empty, and so the minimal action paths with a squared equals minus 1 just won't exist. You'll have to go to the next level. But we're taking these n's to be large, and we're going to take them to be as divisible by 2 as we need. All right. So we found a quaternionic structure. On R2n. That's why n has to be even, because any quaternionic vector space has a dimension which is divisible by 4, has real dimension divisible by 4. And by an argument similar to what I gave before, omega 2 of 2n is equal to the space of all quaternionic structures on R2n compatible with the Euclidean metric. And this will be the unitary group divided by the symplectic group. So my convention is that USP of 2 is SU2. USP 2n is the intersection of U2n with SP2nc. Now, the other half of the world uses the definition that SPn is what I call USPn. USP2n, excuse me. And the reason for that is that SPn can be thought of as n by n unitary matrices over the quaternions. Okay. So this is what we also were calling use of H of n in earlier lectures. So I might also denote this as U of n divided by SP n over 2.
I have a question.
Yeah.
So you fix the J1 to be J there, so you can also allow to vary J1. So it's like this filtration is more.
Well, yeah. So I first, in order to define omega 2, I first fix a J1. This is an important point. And then omega 2 is the space of all possible J2s I can add to that fixed J1. Okay. Now you could change J1, and then you'll get an equivalent omega 2. But omega 2 is not the space of J1s and J2s.
Oh, I thought it's the space.
No, omega 2, this is an important point. Omega 2 is the space of J2s given a fixed J1.
It's not the space of quaternion structures. It's like
No, it is. Okay, I see your point. It is true that it's this homogeneous space. So, yeah, that's a good question. Let me think about that offline. Well, the important thing for what we're going to do right now, I'm pretty sure this is true because it's in Milner's book, but let's just understand why this is true. Okay, so if we want to look at this, we're going to, again, view this space as a homogeneous space where A goes to H inverse A H. Okay? And again, we can now make this transitive, but this H has to commute with the J. So the H has got to be in UN, you see. So it's a homogeneous space for UN, and then I'm done. Okay. Now you say, why don't I also have to move the J1 to get all possible quaternionic structures? Yeah, I have to think about that. Okay. In any case, we have this homogeneous space. Now, again, what did we get before? So we got loops on O was O mod U. Okay, and that was different from the Grassmannian. And so then we looked at loops on O mod U, and then by our usual arguments, now this is going to be U mod SP. But it's still different from the original Grassmannian we had, which was O of n plus m divided by O times O. So we still haven't closed the loop. Okay? So what are we going to do? Well, let's calculate. Let's fix now a J2 in this manifold omega 2 of 2n and compute the tangent space of J2 of omega 2 of 2n. Okay? So let's do that. So now we're going to look at a curve, e to the pi a check, let's call it, times t times J2. That's going to be our curve. Oh, I should have said it's probably completely obvious. So, study paths in omega 2 of 2n from J2 to minus J2 and apply Morse theory to the action principle for that. Now you have two Lagrange multipliers. You have minus trace of G inverse G dot squared. You have trace of lambda 1, G squared plus 1, trace of lambda 2, G anti-commuter with J is 0. Because those are the conditions. And J we're now calling J1. Okay. So now we play the same kind of game. So we say, okay, supposing we have such a path, G of t is e to the pi a check t times J2. Okay, what is the condition that this be in omega 2? And what we find is that, first of all, g of t squared is minus 1, and so that's going to imply, as it did before, that a check anti-commutator j2 equals 0. And we also want that g of t anti-commutator j1 is 0, and that implies that a check commutator j1 equals 0. I'll demonstrate that. Let me put that in here. So if we differentiate this equation with that form up there, we get a check j2 j1 plus j1 a check j2 equals 0. Okay, but a check and j2 anti-commute, so I can change this equation to minus j2 a check j1. Oh, whoops, I didn't want to do that. Let me put that back like that. I can bring the j2 to the right. That's what I want to do. I get a check j1 j2 with a minus sign. The j2 is invertible, and so I see that a check commutes with j1. Now, it's not very pleasant to have a commutator and an anti-commutator here. So let's define instead a is equal to a check times j2, and note the following. A transpose is still equal to minus a, so this guy is in the Lie algebra of O2n, that's good. And moreover, this a anti-commutes with both j1 and j2. Okay, so I'm using the fact that a check commutes with j1. So if I add this extra factor of j2 here, the a anti-commutes. So with that understood, we then have computed that the tangent space at j2 of omega 2 of 2n is the set of A in O2n such that A anti-commutator ji is 0 for I equals both 1 and 2. Well, now the story is exactly as before. So our path, g of t equals e to the pi t a check times j2. It has to go from j2 to minus j2. So a check is conjugate to 0, a1 minus a1, 0, etc. The action of the path is trace. The action of the path is proportional to minus the trace of a check squared, which you can check is the same thing as minus the trace of a squared. We like the a better because the conditions on a are more uniform. Okay? Same story, right? Minimal action paths. So the minimal action paths in omega 2 of 2n from j2 to minus j2 is equal to the space, which we'll call omega 3 of 2n, which is equal to the set of A in the orthogonal group, not the Lie algebra, such that a squared is minus 1, and a anti-commutator ji is 0 for I equals 1 and 2. And I'll interpret this space in just a moment. But at this point, I think the pattern should be clear. So let me make it explicit. So what's the pattern here? Assume n is divisible by a sufficiently large power of 2. Okay. Then there exist complex structures. Let's call them J1, J2, up to Jk minus 1, such that they anti-commute. J sub I with J sub j is minus 2 delta ij, which of course means that we have a Clifford algebra. And R2n is a Clifford module. More on that later. Then we fix these complex structures and we define for 1 less than L less than or equal to K, we define omega sub L of 2n to be the set of matrices A in the group such that A squared is minus 1 and A anti-commutes with J sub j, where J goes from 1 up to L minus 1. So it's the space where if you fix the first L minus 1 complex structures, it's the space of complex structures you have the choice to add at the nth step. Okay? So what are the assertions here? So then we have these submanifolds, this analog of, well, in fact, they are totally geodesic, but we're using the action of classical mechanics. So they satisfy this nice principle that if you take the solution of the equations of motion with initial point on the manifold and tangent to the manifold, then, in fact, it remains a solution of the equations of motion inside that manifold. So we have this filtration of spaces, and the space of minimal action paths from J sub L to minus J sub L in omega sub L is diffeomorphic to omega sub L plus 1. And finally, the non-minimal paths have the number of unstable modes, the downward pointing modes in the sense of Morse theory, grows with n. I can end this here. Okay. So that means that each of these successive spaces is a good approximation to the loop space of the previous one. So now what I want to do is I want to interpret this omega 3 and then say how it keeps going in general. So let's go back to omega 3. What is this space? Okay, so set n equals 8r for some positive integer r. So we just need, I said we need a power of 2. What we're going to need is 16. Okay. Then, having fixed J1 and J2, this is the space of J3s such that we have the Clifford relations, which is the same, in this case, as the quaternion relations. Okay? So if we get a point in this space, call it J3, then we have, okay, J1, J2, and J3 satisfy the Clifford relations. Now, notice that the product of J1, J2, J3 squared is plus 1. You all know that? You should know that from manipulating Clifford algebras and spinors if you've done any calculations of fermions. Okay. This is, I'm going to say a lot of things like this, and these are just easy exercises, so I'm not going to check them, but I leave them to you. This is a good thing for you to check. Okay. So J1, J2, J3 squared is equal to plus 1, so that means we can decompose R, 16R into V plus, direct sum V minus, where this is the plus 1 eigenspace, and this is the minus 1 eigenspace. Of, let's call it J sub 1, 2, 3. Moreover, J sub I commute with J sub 1, 2, 3. Right? Think about that. So J1, I claim, commutes with J1, J2, J3. See, because J1 commutes with J1, and it anti-commutes with J2, and it anti-commutes with J3, so that's two minus signs. So J1 commutes with J1, 2, 3. And similarly, J2 and J3 commute with J1, 2, 3. So therefore, this space is taken to itself by J1, J2, and J3. And this space is taken to itself by J1, J2, and J3. Okay, so that means that implies that R, 16R has a quaternionic structure. It's isomorphic to H for R. And each of these subspaces is a quaternionic vector space. And each of V plus minus is a quaternionic vector space. So that means that omega 3 of 16R is the Grassmannian of quaternionic vector spaces, the total Grassmannian of quaternionic vector spaces on H4R. So that's got many different components. It's the Grassmannian of components 4R plus K, 4R minus K of H. Or, if you prefer, it's SP 4R divided by SP, that's 2R plus K, 2R minus K. Is it wrong in the notes? Indeed, it's wrong in the notes. 2R plus K, 2R minus K. R plus K times SP 2R minus K. We saw that kind of multi-component Grassmannian before. And so what we've discovered then, taking the large N limit, is that the third loop space of O is Z times BSP. So this K, which is going from 0 to 2R, is starting k going from minus 2r to 2r, is starting to become the z as n goes to infinity, or r goes to infinity. And then we recognize the large n limit of these quaternionic homogeneous spaces as BSP. Okay, so we're trying to get back to O. Remember, we want O of 2n divided by O of n times O of n. We've gone 4 steps, and now we've gotten to the SPs. Okay. So that's what this omega 3 is. It's the Grassmannian, the total Grassmannian of all quaternionic vector spaces in a big quaternionic vector space. Okay, so now we could keep going with omega 4, omega 5, omega 6, and omega 7. And for that, I refer you to Milner's book. But I want to skip ahead to the miracle. Okay? The miracle appears at omega 8. Okay? So let's fast forward to omega 8. So let's suppose that we have fixed J1 through J7. Okay, and now we're looking at the space of J8s that we can add. And we want to know what is that space. So that's the 8th loop space. That's the 8th loop space of the orthogonal loop in the large n loop. So we fix J1 through J7, and then omega 8 is the space of possible J8s, in rather colloquial terms. But I've defined precisely what I mean by that. Okay. So the first thing we should do is say to ourselves, well, what does J1 through J7 give us? Okay? And here's what it gives us. Well, first of all, it gave us this J1, J2, J3, which squares to 1. So I could make, for example, a projection operator. Right? I could make a projection operator 1/2, 1 plus and minus, J1, J2, J3. Right? That's a projection operator, and that gives me a decomposition of R, 16R equals V plus direct sum V minus. Now, as I showed, the V plus and the V minus might have different dimensions. They have to have real dimensions divisible by 4 because they're quaternionic, but they're many different components. So choose the k equals 0 component. In other words, the middle component, the one of largest dimension. Okay? Now, let's look at J145, which is J1 times J4 times J5. I claim that, first of all, J145 squares to plus 1. That's 0.1. Well, if you believe me about this, you have to believe me about that. It's just a change of names, right? Okay. What's a little less obvious, and you have to do this in a quiet room, is J145 commutes with J123. But it's not too hard. I mean, think about it this way. If you bring the J1 past this, well, we already knew that J1 commutes with this. If you bring the J2 past this, well, you get 3 minus signs, because 2 is different from 1, 4, and 5. If you bring the J3 through this, you get another set of 3 minus signs. So the 2 minus signs from bringing these two through cancel each other, so it commutes. Should I do that slowly? No? Y'all believe me?
So I can ask you
Yeah.
before. What do you mean by choose the k equal to? That means you pick some j1 to 3 such that this.
That's right. That's right. So what this we've chosen, remember, we fixed j1, 2, and 3. Okay? So we had to make a choice of the j1, 2, 3. So when we make a choice of j1, 2, 3, we get this. A choice of j1, 1, 2, 3 lands us in this space. I'm saying let's choose it. We could have made a stupid choice to put us into the k equals 2r component. Let's not do that. Let's take a choice such that we get into the k equals 0 component. All right, so these commute. So that means we have commuting operators, which square to 1, so we can take the simultaneous eigenspace. Okay, so let's let W, sitting inside V plus, be the simultaneous plus 1 eigenspace of J1, 2, 3 and J1, 4, 5. Now, J2 commutes with J1, 2, 3. So J2 takes V plus to V plus. But J2 anti-commutes with J1, 4, 5. Right? Because it anti-commutes with 1, 4, and 5. That's 3 minus signs. So J2 takes V plus to V plus, but clearly it's going to take the plus 1 eigenspace of J1, 4, 5 to the minus 1 eigenspace of J1, 4, 5. Okay, so that means that with these guys, we have a decomposition of V plus equals W direct sum J2 dot W. In particular, these spaces are isomorphic and orthogonal. So if this was isomorphic to R, 8R, and it is because I chose the k equals 0 component, that implies that V plus is an 8R dimensional vector space. That implies that this W is a 4R dimensional vector space, because the dimensions have to be split evenly. And one more thing to say. J1 commutes with J1, 4, 5. And J1 commutes with J1, 2, 3. So J1 preserves W. All right. Now we do the same thing with J2, 4, 6. So J2, 4, 6 squares to plus 1. And J2, 4, 6 commutes with J1, 2, 3. Why is that? Because there's a common 2 and the other guys are all different. So it's just like the situation we had before. And similarly, J2, 4, 6 commutes with J1, 4, 5 because there's a common 4 and the other guys are different. Okay, so that means we can look at the common eigenspace inside W. So these guys commute, so we can restrict them to W. W is the space where 1, 2, 3 and 1, 4, 5 is equal to plus 1. So we can let X inside W be the space where J1, 2, 3 equals J1, 4, 5 equals J2, 4, 6 is plus 1. Okay. Now, as I just remarked, J1 commutes with these two guys, and so it takes W to W. But you see, J1 anti-commutes with J2, 4, 6. So by the same logic, W is equal to X direct sum J1.x. And so this was isomorphic to R, what did we say, 4R. So this x is isomorphic to R2R. Again, because there's an isomorphism between these two, so they have the same dimension, so the dimension has to split. Now, guess what? We're going to do it again. Okay? So now, look at J167, which is also squaring to +1. And J167 commutes with J123 because there's a common 1 and the others are different. It commutes with J145 for the same reason. It commutes with J246 for the same reason. Okay. So now we can take x and split it into the plus and minus eigenspaces of J167. Okay, so that's the structure we're getting. And that's the structure we're getting from the fixing from the first 7 J's. Now, let's let G equals J7 times J8. Okay. This commutes with 1, 2, 3, 1, 4, 5, 2, 4, 6, but anti-commutes with J167, the last one we introduced. Okay, so that means that this G goes back and forth between these two. So G is an orthogonal isomorphism of x plus to x minus, which means that they have the same dimension. So x plus is isomorphic to R to the R. X minus is isomorphic to R to the R. And two such isomorphisms, of course, differ by an orthogonal transformation on R to the R. So that means now we finally got home. Okay? So let's relish this delicious conclusion that omega 8 of 16R is diffeomorphic to the orthogonal group in R dimensions. Okay? So we had this nested set of omegas. Okay, each one was a good approximation to the loop space of the next. And then after 8 steps, what we discovered is that we got back to the orthogonal group. And that's dot periodicity. Okay, so let me just put up here the conclusion that we got. So if we let, now I'm stabilizing, taking the large n limit. So we have B is Z times BO. Then what we've shown is that the first loop space on B is O. That was the easy part. Then we tried to take the second loop space on B, which was the first loop space on O. And we failed to close the loop. Instead, we got O mod U. Then we tried again. Omega 3 on B, which was the second loop space on O. We failed again. First we got the space of complex structures, then we got the space of quaternionic structures. We tried again. That was the third loop space on O. That's our omega 3 up there. And that was Z times BSP, the Grassmannian of the quaternionic vector spaces. Well, I said you can look up the other ones. I'll just write the answers. So omega 5 of O is SP. That's not a surprise because this is BSP. So we sort of knew that it had to happen because the loop space on BSP is SP. Omega 6 of B is SP mod U. omega 7 of B is U mod O. And finally, I just showed you that omega 8 on B is B. If you like, because omega 8 on O is O. So this closes the loop. All right. Now, there are lots of beautiful proofs. Let me just make a few remarks. There are lots of beautiful proofs of Bott periodicity. We are really close to the whole subject of K-theory. Most of those proofs involve K-theory. But there's one other approach that I want to mention. There's one other approach I want to mention briefly. So as I said, we have the easy fibration. Unitary goes to contractible, goes to Grassmannian. And what we'd like is to find the hard one, the Grassmannian, as a fiber of some contractible space projecting over the unitaries. And if you can do that, then you have Bott periodicity. So now I'm back with the complex case. Of course, something similar could be said in the real case. So one way to achieve the second thing, a different way from what we've said, is to do the following. Let H of n be the space of all n by n Hermitian matrices with eigenvalues between with eigenvalues in the closed interval from minus pi to pi. And let's observe that this is a contractible space. Because you see, if I have two such Hermitian operators, right, if I take their operator norm, then by the triangle inequality, we can write this, which is less than or equal to pi. So the space of n by n Hermitian matrices with eigenvalues between plus and minus pi is a contractible space. Okay. So now let's consider the map P sub n, which goes from h of n to un, which takes a, in this Hermitian operator, to the exponential of ia. Okay? So you can take a Hermitian operator, you can exponentiate it, and get a unitary operator. This is onto, but not a fibration. You can see that there's going to be some problems. For example, if we look at minus, if we take some unitary matrix close to the identity, then it is onto and into, right? It's a diffeomorphism. That's the Lie algebra mapping diffeomorphically into the group, right? So if your unitary matrix is close to the identity, then there's a unique A that satisfies this. However, supposing we went all the way to minus 1, what would A be? Well, A would be anything which was conjugate to pi times plus 1 k minus 1 and minus k. Right? So the fiber, P sub n inverse of minus 1, is equal to the Grassmannian, the total Grassmannian in Cn. Well, that's sort of what we want, right? We want a Grassmannian into a contractible space projecting to unitaries. But this is only true at minus 1, and it's very far from being true near 1. So what we do is we stabilize. So we map Hn into Hn plus 2 by taking A goes to minus pi A pi. And we map U of n into Un plus 2 by taking little u goes to minus 1 u minus 1. Actually, I should have said, in general, Pn inverse of little u is equal to the Grassmannian of the eigenspace, the minus 1 eigenspace of u. That's the general result. Okay. Now, we stabilize. We keep embedding this. Okay, so we go minus pi a, pi, so on. Minus 1. And now what you see is that in the limit, most of this unitary matrix maps to minus 1, is in minus 1, right? All but a finite piece. So it stands to reason that the inverse image is some kind of infinite Grassmannian. And so what you get here is something called a quasi-fibration, which is not a fibration, but it satisfies the long exact sequence in homotopy, and that's all we needed here. So that's another way to try and prove Bott periodicity. Now, I have to talk about the Clifford algebras. I mean, it's obvious from what we've just said that the Clifford algebras are deeply involved here. So let me say just a few words to finish up the lecture about this. Okay, so let me remind you that Clifford of n is the algebra which is generated by some e sub i's, I equals 1 up to n, subject to the relations ei, ej is minus 2 delta ij. We only need this signature. So in my group theory course, I do Clifford algebras in all possible signatures, but this signature for what we're doing is what we need. Now, you can think of these, obviously fermions are lurking in the background here. If you think about this algebra, you can generate it out of the EIs. EI squared is minus 1, so you can have either an EI or not. And you can get a basis for the algebra by just multiplying different EIs. Okay? And so the dimension of this Clifford algebra over R, Clifford n, is 2 to the n. Clear enough. Now, famously, these Clifford algebras form a mod 8 pattern that looks like R, C, H, H plus H, C, R, R plus R. And then back to R. So in the notes, I give you the table of the first 8 Clifford algebras. And I also list the smallest dimension. Let's let AN be the smallest real irrep of the Clifford algebra. And I also give you the Grothendieck group of the representations, or if you like, the representation ring. So most of the time, there's only one unique, irreducible representation, except in these cases when there are 2. And finally, we have the periodicity. Clifford n plus 8 is Clifford n tensor R of 16. Should sound familiar. And similarly, A sub n plus A is therefore 16A of n. Because it's late, I'm not going to copy the table and the notes onto the board. But I'm also going to cut corners right now by doing the easier complex case. So if we take the complex Clifford algebra, so that's Clifford of n tensor with the complex numbers, then the mod 8 periodicity collapses to a mod 2 periodicity. Should also sound familiar. And we have Clifford of n plus 2 is Clifford of n tensor the 2 by 2 matrices over the complex numbers as an algebra. So now we can make a little table here of n, Clifford of n. I see there's a mistake in the notes. It should be complex Clifford in that table. And similarly in the last column. A sub n, which is now the minimal complex dimension, and the Grothendieck group of Clifford n modules. Okay? So now we have to distinguish between even and odd dimensions. Okay, so in this case, the Clifford algebra is isomorphic to the complex algebra of 2 to the p by 2 to the p matrices. So that means the minimal irreducible representation is 2 to the p dimensions. That's complex dimension. There's a unique representation. Call it delta sub p. Now in the 2p plus 1 case, there are 2 factors here, which you can distinguish by the sign of the volume element, E1 through E2p plus 1, which is either plus or minus 1. Oh, you might have to multiply by some powers of I to get the right, correctly normalized volume element. Again, the minimal dimension is 2 to the p. And now there are 2 in equivalent Clifford modules, delta p plus and delta p minus, according to the sign of the volume element. Okay, so obviously there has to be a relationship to Bott periodicity. Saying what it is a little tricky. So I'm going to tell you one beautiful relation which appeared in a famous paper by Atiyah, Bott, and Shapiro. So that's the paper I'm going to tell you a little bit about right now. Okay, so let's consider a rep of Clifford of v dimensions by gamma matrices. So we have gamma mu, gamma nu is minus 2 delta mu nu, and the gamma mu's are anti-Hermitian. Okay, and the mu and nu run from 1 up to d. Now, suppose that x naught and x mu are coordinates on the sphere, the unit sphere, SD, embedded in RD plus 1. Okay, so x naught squared plus x mu is 1. Let us consider the function t of x, which is equal to x naught times 1 plus x mu gamma mu. Okay? I claim that t of x dagger is equal to 1. Can you see why? Should I do that? So that's x naught plus x mu gamma mu. Now I take the anti-Hermitian, these are anti-Hermitian, so this is x mu gamma nu. So this is x naught squared plus x dot gamma minus x naught times x dot gamma minus x dot gamma minus x mu gamma nu. Cross terms cancel. And now here I can use the Clifford relations. So you see this is symmetric on mu and nu are not equal. And the gamma matrices anti-commute, and then they square to minus 1. So this is equal to x naught squared plus x mu, which is 1, as I claim. I'm desperate for a piece of chalk. Let's see. Maybe there's one. All right. Okay, so that means this T of x is a unitary matrix. So T defines a map from SD into the unitary group. Well, 2 to the d over 2, if I choose the irreducible representation, but u to the v, u of unitary group on a vector space V for any representation. I didn't use what particular representation I need, but if I chose the minimal one, the spin representation, then it would be into this unitary group. Now, let's ask if this is topologically non-trivial. So this defines an element of pi d of the unitary group of u to the 2 to the d over 2. So that's certainly in the stable range, so that's pi d of u. Well, let's look at some examples first. So supposing d is equal to 1, okay? So we just have gamma squared equals minus 1. Well, there are two irreducible representations, okay? They're one-dimensional, and gamma is plus or minus I, right? So now, what is t of x? Well, t of x is equal to x naught plus I x1 if I choose gamma equals I, and x naught minus I x1 if gamma equals minus I. And remember, x naught squared plus x1 squared equals 1. This is the unit circle mapping into u1. And you see this surely is homotopically non-trivial. This is winding number 1. All right? Let's take d equals 3. Then we can take the gamma i's to be the square root of minus 1 times the Pauli matrices. That's a representation. And then we can take t of x to be x naught plus xi times the square root of minus 1 sigma I. Well, that is a representation of SU2. Okay? So that maps S3 to SU2 with winding number 1. Okay? So that, again, constructs a non-trivial element that indeed constructs the generator. Of pi 3 of SU2, which is Z. Okay, now you could ask, when is this homotopy class trivial? Okay, so in these two cases, I got the generator of pi 1 of U1. I got the generator of pi 3 of SU2. We could ask, when is T of x defining the trivial homotopy class? Okay, and now there's a very easy criterion. So here's a criterion for triviality. Suppose we can introduce another gamma matrix. Let's call it just capital gamma, which is 2 to the d over 2 by 2 to the d over 2, and anti-Hermitian. So gamma dagger is minus gamma, gamma squared equals minus 1, and gamma mu is 0. Okay, in other words, supposing I could make my Clifford algebra, I could extend on the representation that I started with. This is crucial. On the representation I started with, supposing I could introduce another matrix, gamma. Well, now we could look at the d plus 1 dimensional sphere, x naught, x mu, and y, such that x naught squared plus x mu plus y squared equals 1, sitting inside R d plus 2. And we could define t tilde of x and y to be x naught plus x mu gamma mu plus y times gamma. So this is still in the unitary group 2 to the d over 2. Now, it's defined on this sphere SD plus 1, and supposing the vertical direction is the y direction, then the equator here is SD. This is y equals 0. And what happens at y equals 0? Well, at y equals 0, we have our map T of x. On the other hand, we can view y as a smooth homotopy. You see, up here we have x naught equals x mu equals 0 and y equals 1. And so that's a smooth homotopy to the constant map. So in that case, it must be true that indeed T of x is homotopically trivial. So if the irrep of Clifford of D is the restriction of an irrep of Clifford of D plus 1, then T of x is topologically trivial. Now, everything I've said here applies, of course, to the real case, too, with, I hope, obvious modifications. Now, also, I didn't have to fix on this particular representation, as I just remarked over here. So, more generally, if V is any rep of the EIs of Clifford, we can